Welcome to the second lecture in the subject Basics of Molecular Modeling of Drugs that will be focused on uh, interactions of drugs or potential drugs. Generally, we can talk about ligands. And on the other side, there will be the structure of any macromolecular target in the body or in any organisms. So we will be talking about the structure of proteins, the function of enzymes, and nucleic acid structure. The structures that act as targets for drugs can be divided according to their character into proteins, nucleic acids, lipids, or carbohydrates. The last two items are less often. The most often target for drugs are proteins. And this can be enzymes, receptors, transport proteins, structural proteins, and maybe also some other type of proteins. Nucleic acid are not as often as proteins as target. However, it is typical for example, for anti-cancer treatment. There is always a binding site in the target that enables the interaction with low molecular drug. So let's talk about the binding. There are always important structural features in the drug or generally any ligand that binds to the active site of the target. So we have the figure below where it's visible that the binding site does not perfectly fit to the drug. However, today, the theory of induced fit is acknowledged. It means that the macromolecular target can adopt during binding to the drug shape. So in the detail up, you can see that there are 5 interactions between the drug and the target. So it means there are some functional group on the drug side and on the target side that can enable the interactions and bind the drug in the active site for some specific time. You can see also that the shape of the binding site was changed. It looks a little bit different before the binding and after binding the drug. So this is the induced fit mode. Let's talk now about the types of the interactions. So generally, we can divide them into 2 groups. There are plenty of non-covalent bonds that can proceed between the drug and target. And there can be also covalent bonding, which is much stronger, but not as so often. You can see also the energy of binding, covalent binding, which is represented by 200 to 400 kilojoules per mole. However, as I said, it is not as often as the non-covalent interactions. We can include their electrostatic bonds, I mean the ionic bonds, hydrogen bonding, halogen bond, and some weaker types of interactions, for example, dipole-dipole interaction, van der Waals interactions, or hydrophobic interactions. So now we will discuss these types of interactions more in details and explain them. I would like to tell something about the covalent bond. That was taboo actually in the history. However, there were some drugs used in the past and it was not known that they bind covalently to the target. The very old example is the acetyl salicylic acid called aspirin with the proprietary name marketed by the company Bayer at the end of 19th century. Then, for example, penicillin binds as well to the target via the covalent bond, esomeprazole as well. But in the history, it was unwanted to create the covalent bond between the drug and the target, because there was a fear that the drug will be too promiscuous and it will be able to bind to different targets and cause many adverse effects. Recently, actually, it started to be a trend to create and design covalent binders and tune especially the binding to the only target based on the structure. So maybe from the year 2000, in the plot on the right side, you can see the frequency of appearance of covalent binders in patent applications. So you can see the increase. And as for the examples of the drugs, we can mention, for example, bortezomib, ibrutinib, saxagliptin, dacomitinib, and voxelotor. In the year 2020, there were 35 drugs registered by FDA from the group of covalent binders. And I think the most typical indications is cancer treatment. And we can see the progress in drug design that's from something what was taboo in the past became a trend recently. I have special lecture in another subject called current trends in the development of chemical drugs, focused only on covalent binders and the structural design and more examples. So now I would like to turn your attention to the most often non-covalent interactions. So let's talk about the electrostatic bonding, which is typically the ionic bond. It is the strongest non-covalent intermolecular bond, and you can see and compare the strength of the interaction with the covalent bond, which is tenfold less than the covalent binding. So it is generally known that it's the interaction between negatively and positively charged parts in the molecules. You can see both the types where the negative charge is in the drug or in the target. So it's very strong interaction, and it is even stronger in hydrophobic environment. Another type of non-covalent bond is the hydrogen bond, which is very important for drug action. And we can define it as a dipole-dipole interaction between an electron deficient hydrogen that is bound typically to oxygen or nitrogen, generally any electronegative atom. This is the hydrogen bond donor. It affords the hydrogen into the bonding, and the other partner is an electron-rich heteroatom. Typically, oxygen or nitrogen on any atom, any atom with lone pair of electrons, which represent the hydrogen bond acceptor. So generally, we can say that is a weak interaction. However, there proceeds sort of orbitals overlapping, which can be seen on the figure on the right bottom side. So on the left side, we can see the hydrogen bond donor and interacting with hydrogen bond acceptor, and we can see that there is an orbital overlap. Generally, we can represent the structure as it is visible in figure 1.6. The strength of this interaction can vary depending on the functional group that is involved in the interaction, on the distance between the two interacting functional groups in the target and in the ligand, and also on the angle, how do the interacting partners come together. So we can generally say that in case there is the angle 180, which means that the functional groups are ideally in one line. It is depicted in the right upper figure. It is the strongest type of interaction. However, when the interacting partners come together in the angle 90 degree, it is less strong. So it is reflected in the energy. It might be 16, but it might be also 60 kilojoules per mole, which means that this type of interaction might be under ideal conditions even stronger than the hydrogen bond. Let's talk a little bit now about the functional bonds that are involved in the hydrogen bond. It is typical that the hydrogen bond donor is the hydrogen in the hydroxy or amino group. However, this functional group can act also as acceptor of hydrogen bond due to the presence of lone electronic pair on the oxygen or nitrogen. It is called hydrogen bond flip-flop. So these functional groups can be acceptors as well donors of hydrogen bond. As for the strength of hydrogen bond acceptors, the strongest ones are the carboxylates. I mean the ionized carboxylic acids or ionized phosphate. Moderate hydrogen bond acceptors are non-ionized carboxylic acid, alcohols, ethers, amines, carbonyls like ketones, and ester or amines. As for the weak hydrogen bond acceptor, we can talk about sulfides, fluorides, chlorides, and some hydrophobic parts. With focus on carbonyl compounds, the strongest hydrogen bond acceptor is the ionized carboxylic acid. Then we can count the amide as the second strongest in the row. Then carbonyl compound, and the least is the ester. So you can see the direction of the strength of hydrogen bond acceptor. As for nitrogen-derived compounds, tertiary amine is a good hydrogen or relatively good hydrogen bond acceptor, whereas amide nitrogen is less active, but there can be the carbonyl oxygen as acceptor. So we already mentioned amides among the carbonyl compounds. So it is more probably that the oxygen will be the acceptor of hydrogen bond rather than the nitrogen in the amide bond. As for the aniline, and the nitrogen in aniline is a poor hydrogen bond acceptor. So it is again somehow ordered here according to the hydrogen bond acceptor strength. And as I mentioned, this type of interaction is very important, especially for acting on drugs. It might be responsible for intermolecular interactions. So, for example, between water molecules, which results in high boiling point of water. And hydrogen bond is also responsible for intramolecular interactions, which is typically, for example, for the targets, you know that proteins can be folded due to the hydrogen bonds. The double helix in nucleic acids also holds together due to the hydrogen bond. So we will see it later when we will be talking about the drug targets. I would like to mention something what might not be known for you, and it's fluorine as hydrogen bond acceptor. So the fluorine in the substituting any carbon can accept hydrogen bond donor and create hydrogen bond. But there are some conditions. So high concentration of hydrogen bond donor is required, and absence of any other strong hydrogen bond acceptor. Under these two conditions, the fluorine can create hydrogen bond with any hydrogen bond donor. So it can also proceed in protein pockets, and it can play a role in the interaction of drug and any macromolecular target. There is a publication, an article, where the researchers measured the strength of differently substituted fluorinated compounds, and they have found that the fluoromethyl substitution a stronger hydrogen bond acceptor than polyfluorinated substituents. Let's talk now about halogen bonding. So we, until now, we mentioned the covalent bond, ionic bond, and hydrogen bond. And something what was revealed also in the last history is the halogen bond. It is a non-covalent interaction occurring between region of positive electrostatic potential of a covalent bonded halogen atom and an electron-rich atom on the other side. So typically, the halogen bond donor can be chlorine, bromine, or iodine. The last one is the strongest halogen bond donor. And the interacting partner as halogen bond acceptor can be oxygen, sulfur, nitrogen, or aromatic p electron system. The principle of the bonding is based on the fact that halogen creates on the C halogen bond so-called sigma hole, which is created due to the electron displacement around the halogen atom. So I will show some pictures in the last row here in this slide. You can see the definition. It's of sigma hole. So it is a small positively charged area at the tip of C halogen bond extension that is then able to interact with oxygen, sulfur, nitrogen, or some aromatic systems. And we can see here in the picture electrostatic potentials of differently substituted methanes. Tetrafluoromethane has no sigma hole at the end of C halogen bond, whereas in case of fluorinated methane, there is visible the yellow region where some positively charged region is obvious, and it is more visible for brominated trifluoromethane or even iodinated trifluoromethane. So the iodine would be able to create the strongest halogen bond because the region of the positively charged is the biggest. As for the interacting partner, it's the most often carbonyl oxygen in the protein backbone. For example, asparagine, glutamine, aspartic acid, or glutamic acid side chain. This interaction was revealed in X-ray crystallography, and it is used in drug design. I have one example. One is from measurement between acetone and bromobenzene. So you can see some electrostatic potential and the visible sigma hole. It has different colors than in the previous picture. So you can see the range of the charges. And on the right side, you can see a picture from Parisi article where the interaction between diclofenac, which is an anti-inflammatory non-steroidal drugs, interacting with cyclooxygenase. It's the target of this non-steroidal anti-inflammatory drug, and there is a halogen bond visible between the chlorine of diclofenac and the serine a hydroxy group in the cyclooxygenase structure. So it was halogen bond, and let's talk now about dipole-dipole or ion-dipole interactions. It is obvious that the ion-dipole interaction will be stronger than dipole-dipole interaction because there is one charge in the interaction, and the dipole-dipole interaction is based on the permanent dipole in the drug. For example, this carbonyl compound, and dipole moment that is permanently present in any functional group in the binding site. So it is clear, I think, and we will be talking also about van der Waals interactions. They can proceed between hydrophobic regions in the drug and in the target, and it is based on creating some interaction between the transient or temporary dipoles. So generally, there is no permanent dipole in the structure. However, due to the electron movements, there can be a transient dipole can be induced, and it can induce a temporary dipole also in the interacting partners. So you can see in the figure, in the first part, there is no interaction. In the middle part, there is an temporary dipole that was created in the drug due to the electron fluctuation. And this transient dipole can induce a dipole in the binding site and show some this type of weak interaction that is called van der Waals interaction, and it belongs to a larger group of interactions called London forces. And last type of interaction is PP interaction, which is the interaction between completely hydrophobic parts of the molecule. We have the example of benzenes here. The strength of the interaction depends on the distance and also on the angle how these two parts come together. So the most strong PP interaction would be the sandwich type. The second strongest would be the T shape, where you can see there is an 90-degree angle between the two interacting benzenes, and the least strong interaction would be parallel displaced, would be the interaction between the two benzene rings in the displaced arrangement. So we talked about covalent bonds, different types of non-covalent bonds, for example, ionic, hydrogen bond, halogen bond, dipole-dipole interactions, and van der Waals forces, as well PP interactions. So when we conclude, we can say that the covalent bond is the strongest type of interactions, but it does not proceed as often in the interaction between drug and target. So its importance is not as high as electrostatic or hydrogen bonds or hydrophobic interactions. So they are more often, even though the energy is relatively low. However, there are always several interactions in case of non-covalent interactions between the drug and the target. So around three pieces of non-covalent interactions, up to 4, 5, or 6. So the more interactions between one molecule of drug and the target, the stronger binding to the target. On the right side of the slide, you can see some tables with the energy data concerning the particular types of interactions. So they can vary a little bit depending on the source, depending on the type of measurement. It can be given sometimes in kilojoules per mole, sometimes in kilocalories. So be careful also about the units. However, I think that it is obvious that we went during the lecture from the most strong interaction to the least strong interaction. There are also some other aspects of binding between drug and target, and it is the repulsion. So in case there are equally charged parts of the molecule in the target as well in the drug, there would be a repulsive interaction. So it means no interaction would, no binding will proceed. And something what is very important is solvation with water. So we have to consider that the drug is given to the patient in a very, very low amount. It means that in the water environment, in the organism, it's diluted. And every molecule after the tablet decomposition and dissolution, every molecule becomes of the drug becomes solvated with water molecules. So when we consider the binding to the target, there is a desolvation energy necessary for the binding. So the condition for any binding drug to the target is that the binding energy is greater than energy required to desolvate both the drug and the binding site, because also the target and the binding site is solvated with water. Water solvates differently some hydrophilic part of the proteins and of the drugs, whereas in case of hydrophobic regions, the water molecules are differently ordered. They are more ordered in the layers next to the nonpolar surface. So during binding the drug to the target, we have to consider so-called energy penalty that is paid for dissolution of both the interacting partners before the interaction between them proceeds. On these two pictures that were adopted from the cited textbook, we can see the surface, a surface of binding site of chymotrypsin and the drug, the inhibitor that is bound to the active site. Uh, on the left side, we can see the solvent accessible surface where water molecules are taken into account, which means the binding site is solvated. Whereas on the other side, on the right side, the surface is desolvated. So generally talking, the van der Waals surface, we will be creating also some volumes for proteins during our seminars. So the van der Waals surface is based only on the protein structure. And solvent accessible surface takes into account also the solvation, and it excludes some very small cavities where the water molecule cannot be pulled. You probably know the equation for Gibbs free energy of binding. This energy is dependent on enthalpy, entropy, and temperature. And in the second line, you can see the dependence of Gibbs energy of binding and the binding affinity, like the binding constant K. And from the mathematical expression, it is obvious that small changes in binding energy cause exponential changes in binding affinity represented by the constant K. The prediction of Gibbs free energy is complicated. However, there is a method for its prediction, and it's the free energy perturbation. So generally, what drives the binding of drug and target or any interacting partners in gas phase? The non-covalent association is driven by polar and electrostatic interactions. However, in water phase, in water environment, hydrophobic interactions drive the intermolecular interactions. So that was for the interactions and for the details concerning the bonding. So we discussed the several types of bonds, and we also discussed the solvation with water molecules. And now we will be talking about the structures of the target. So we will revise what you already know from biochemistry, and it's the protein structure and nucleic acid structure. So you know that the primary structure of protein is based on the amino acid sequence in the protein chain. So it's the order of the particular amino acids in the structure. It's based on covalent bonds. As for the secondary structure, there might be either the alpha helix or beta pleated sheet, and it is based on the non-covalent interactions. Then we can recognize some structural motifs or structural domains in the tertiary structure, and they are also based on non-covalent interactions. Quaternary structure is typical for some proteins where more protein units are associated together. So let's go now through the particular type of protein structure. So I think primary is obvious, secondary as well. It is based on hydrogen bonds. And it can be based also on some disulfide bridges in case of cysteine presence in the amino acid sequence. The tertiary structure is based on long-range non-covalent interactions. And tertiary structure is present only for some proteins where we can recognize multiple subunits. So let's talk about the peptide bond, which is actually an amide bond. However, there is something typical for the peptide bond, and it's the shift of electrons from the double bond between carbon and oxygen to the oxygen, which causes the shift of a lone electron pair from nitrogen to the bond between carbon and nitrogen, which results in the double bond between carbon and nitrogen, negatively charged, and it's the cause why the peptide bond, I mean the angle from oxygen to carbonyl carbon and the nitrogen, there is no distortion, no bond angle, and these bonds are planar. So the peptide bond is planar, and there can occur so-called pseudo-isomerism. And we can talk about trans conformation S and cis conformation. So most often there is a trans pseudoisomerism on the peptide bond in proteins, and very rarely we can observe the cis pseudoisomerism, and it is typical for proline amino acid. Because in case of proline, the spatial arrangement is very suitable for the cis arrangement, whereas in case of the other amino acids, there would be a clash and the cis conformation is unfavored. So most often the peptide bond is in the pseudotrans, like the zigzag arrangement, due to the presence of the side chains that are bulky, and it is not favored the cis conformation due to some steric clash. We should revise a little bit biochemistry and talk about the character of the side chains in amino acids. So we can divide them generally into polar amino acids and hydrophobic amino acids. So as for the first type, we have some special cases where the side chain of polar amino acid is charged or it is uncharged. So talking about the positively charged amino acid, we can give examples and we can include arginine, lysine. They have enough high pKa value for the basic functionality, whereas histidines pKa on the imidazole is 6.04, which means it can be partly positively charged and partly non-ionized under physiologic conditions. As for the negatively charged amino acids, we can include aspartic acid and glutamic acid. And that's all for the charged amino acids. Talking about the polar but uncharged amino acids, we can mention the hydroxylated amino acids, serine and threonine. And as for the other amino acids, these are the amide substituted amino acids, asparagine and glutamine. There are some special cases of amino acids. So cysteine would be weakly acidic. However, the sulfonyl group is sometimes or often involved in disulfide binding, and it's responsible for the shape of the protein also. Another special amino acid is the selenocysteine, and two amino acids. Proline was already mentioned that the pyrrolidine nitrogen is involved in the peptide bond, and it enables, due to the steric arrangement, the cis pseudoisomerism for the peptide bond. And glycine is the amino acid that has no side chain, and it is typical for some disordered region or some turns or loops in the structure of proteins. And we should not neglect the aliphatic and aromatic amino acids that belong to the group of lipophilic amino acids, and they are represented by the simplest one, which is alanine, or some more branched amino acids as valine, isoleucine, leucine, or methionine. The special case are amino acids containing the aromatic side chain. for example, phenylalanine, and others are tyrosine tryptophan, whose side chain contains hydroxy or amino group. In case of tyrosine hydroxyl, it might be very slightly acidic.